Hi, Math B. We are doing lesson 4.1c, solving simultaneous linear equations by graphing. So it's really important that we're graphing precisely when we do this. So go ahead and take out your notes and be following along and writing this down as you're watching this video. So number one, consider the linear equations 2x plus y equals 4 and y equals 4x minus 2. I really recommend that if you have access to two different colors that you use them, just so that it helps you kind of keep track of both. Graph both equations on the coordinate plane below. I'm going to start with just this one just because it's already in slope-intercept form for us. Y equals 4x minus 2. Remember, y equals mx plus b. This is my y-intercept. That's where I start my graph. In this case, I'm going to start my graph right at -2. And then my m is my slope. So my 4 is my slope, which means that m is actually 4 over 1 because we want to go rise and then run. So I rise by 4 and then go over to the right in a positive direction by 1. Again, 1, 2, 3, 4, and then over by 1. You could also go down by 4, but you would need to go to the left because this is a positive slope. So we still want our line to look like it's in the positive direction. Hopefully you have a ruler so that your line is much straighter than mine. Second line, I want to get this into slope-intercept form, which means I'm going to subtract 2x from both sides because I want the y to be alone on one side of the equation. So then I have y is equal to -2x plus 4. Now my y-intercept starts at +4, and my slope is going in the opposite direction because it's -2. So I go down by 2 and then over by 1. Whenever you hit a point of intersection, I would put a little star on it so that you know that's your point of intersection. Again, down by 2 over 1, down by 2 over 1. You could also go up 2 over 1 this way, and then you're just going to want to go ahead and draw your line. Okay, so state the coordinates of the point of intersection. That's why we want to put a little star so that we can go ahead and state that it's always going to be x, then y. So from my origin, I go out 1. So that's my x value, and up 2. So the coordinates of the point of intersection is 1, 2. Using the original equations, verify that the point of intersection satisfies both equations. This is asking, is this really a solution to each of these equations? Because this point has to work when I plug it into both of these equations. So that means that I need to plug in 1 for my x and 2 for my y, 1 for my x and 2 for my y. So on my red equation, it's 2 times 1 plus 2 equals 4. So then I'm going to say 2 times 1 is 2 plus 2. So yeah, oops, 2 does not equal 4. 4 equals 4. So then if you get something like that, then we're verifying. Happy face. Next equation, y is equal to 4 times x minus 2. So now 2 equals 4 times 1 is 4, 4 minus 2 is 2, so it works. So this point satisfies both equations because it's on that line. So the only way you ever have a solution is if it works for both. Okay, in the example above, the point of intersection is a solution to a system of equations for both of these graphs. The solution to a pair of simultaneous linear equations is all pairs, if any, of numbers that are solutions to both equations that satisfy both equations. When solved graphically, the solution is the point or points of intersection. So we've kind of gone over this a little bit in class. If they cross at one point, there's one solution, just like the graphs in number 1. If it's the same line, those are going to be overlapping, and they're going to have an infinite number of points where those graphs touch. If the lines are parallel, no matter how they look, they're never going to touch, so they have no solution. So number 2, use the given system to complete the following. Graph the system. Again, I'm going to use different colors to break this up. So we're going to start with y equals 2x minus 5. I would really encourage you to pause the video here and graph this on your own to make sure that you can check that you can graph this on your own. Okay, so y equals 2x minus 5. I'm always going to start at my y-intercept. In this case, in the y equals mx plus b, my b is at -5. So make sure if it's that negative number that you start at -5, not accidentally +5. My slope has to go in this direction since it's +2. So my slope is 2 or 2 over 1. So up 2 over 1, up 2 over 1, up 2 over 1. And I would always encourage you, when you're doing systems, you can also go down 2 over 1 in the other direction. Plot a few more points than you need so that you can be absolutely sure that it's the right point that you're choosing when you say your solution. Okay, our other equation. Now I'm going to start actually at +5 because my y-intercept or my b value is +5. My slope is now -4 over 5, so it's going to go in the opposite direction. I'm now going to go down 4, 1, 2, 3, 4, and over all the way by 5. Down 4, 1, 2, 3, 4, over all the way by 5. I could also go up 4 if I wanted, 1, 2, 3, 4, and over by 5 that way. And as you'll notice, I did not plot a point that also landed on my orange line. So when I draw my line, that point, whatever I hit, it's going to be a fraction, right? I didn't plot an exact point. So I don't know what my solution is yet. But it asks, is 4, 2 a solution? Because if we look at it, it kind of looks like it's a solution. But we have to justify it algebraically. So 4 was our x and 2 was our y. That means that point has to work in both of these. So that means that y would have to equal 2 when x equals 4. If I plug in both of those points, this is 8 minus 5. Well, 2 does not equal 3. So that point is not on my orange line. Let's see if it's on the purple line. I'm going to plug in 2 for y, and I'm going to plug in 4 for x. Well, 2 is equal to -16 over 5. I'm going to try and add -16 plus 5. -16 over 5 plus 5, but I'm going to make the 5 into 5 over 25. -16 plus 25 is 9 over 5. I know 9 over 5, that's not equal to 2 because I know 10 over 5 is equal to 2. So this point is actually not on either one of these lines. Even if it was on one of the lines, it still would not be a solution because it's not on either one of the lines. So you can say, no, this is not a solution. All right, next page here. So 3 and 4 are asking us, determine whether the given point is a solution to the system of linear equations. Justify your answer by checking both equations. Show all of your work. So this is a great question for a quiz or test. Is this point a solution to the system? So don't overthink it. If something is a solution to a system of equations, that means that point has to be on both of these lines. So when I plug it into both of these lines, it has to work. So for number 3, my x value is 1 and my y value is -3. So all I'm going to do is plug in this point 1, -3. So x is 1 and I make my y -3. Well, 1 plus -6 is not going to equal -8. when I plug it in here. 4 plus 4 times 1 plus negative 3 is equal to 1. So 4 plus negative 3 is equal to 1. Well, 1 is equal to 1, so that works. And I just realized I made a mistake. Anybody catch my mistake? It's going too fast for this. I hope that you caught my mistake. 3 times negative 3 is actually negative 9, not negative 6. So 1 plus negative 9 is actually equal to negative 8. So that point is actually on that line, and it's on that line. So make sure that you don't do like I did and actually carry out the final step of each problem. So I can say that this point is a solution because it is on both lines. Again, great question for a quiz or test. We're going to skip number 4. You guys can do number 4 when you're studying for the quiz. That would be a great question to star and come back to. For number 5 and so forth, says graph the given equations on the same coordinate plane to find the solution. Label your lines. Verify algebraically that the solution satisfies both equations. So that means that the first thing I have to do is graph both of these. And the way that I'm going to graph these is by getting them into slope-intercept form. So I'm going to go ahead and put this into slope-intercept form. Well, I would have to subtract x from both sides because I want to get the y alone. So this equation would be y is equal to negative x plus 6. So that's my first equation. I can go ahead and graph that if I want. I start at 6 for my y-intercept, and I always think about which direction is my slope going to be in. It's negative, so that means I go down 1 over 1, because when there's a negative in front of x, it's basically saying that my slope is negative 1 over 1. So down 1 over 1, down 1 over 1, down 1 over 1, and so forth. So then I'm going to go ahead and draw my line. And my other equation, I need to first subtract 2x from both sides to try and get this into slope-intercept form. I'm trying to get it to look like y equals mx plus b so that I can use the slope and y-intercept to graph. So now I have negative 5y equals negative 2x plus 5. I'm trying to get rid of that negative 5 now, and right now it's being multiplied by the y. I have to divide everything by negative 5 to undo that multiplication. So negative 5 divided by negative 5 will cancel. I just have y equals negative divided by negative is going to be 2/5 x. And 5 divided by negative 5 is just going to be negative 1. Go ahead and try and graph this. Pause the video, and we'll come back to it. Okay, when we graph this, we start at negative 1. And then it's a positive slope, so I go up 2 and over 5, and as you'll see, I actually land on a point that's on that graph, so that's going to be my solution. Again, I can go up 2 and over 5, or down 2 and over 5 in this direction. And my graph is going to look like this. Super important to be very precise when we plot that point, because we need to make sure that we get that right solution. So my x value for this is 5, and my y value is 1. So I'm going to do this not yellow. My solution is 5, 1. And when you verify that, I need to be able to plug it into both equations to double check that I didn't accidentally graph incorrectly and that that point is actually on both of these lines. So plugging in 5 for x, 1 for y, 6 does equal 6, so that point works on that line. Plugging in 5 for x here and 1 for y here. So 10 minus 5 Well, that is also going to work on that line. So go ahead and try number 6 on your own. You're going to start by graphing both of these lines and make sure that you're using the y-intercept and the slope to graph both of these lines, and then state the solution. Remember, when there's nothing being added or subtracted, that means that our b value is just 0. So you start your graph at 0 for that one. Go ahead and check your graph now. And you should go ahead and write what your solution is if you haven't already. So our solution is 2, -4, because my x value is 2 and my y value is -4. Remember, we always write xy, not yx. Okay, moving on. Obviously, you would always verify your solution, but for the sake of this video, we're going to move on to number 7. So for number 7, again, we're going to try and get these both into slope-intercept form. So it's nice that they already gave us one in slope-intercept form. You can go ahead and graph that. Start your graph at 4, go up 2 over 1, up 2 over 1, up 2 over 1, or down 2 over 1 in the other direction. And your graph is going to look like this. Hopefully you have a ruler if you're doing this on paper. For this one, I need to get into slope-intercept form. So I need to actually add 2x to both sides. So I have y equals 2x minus 1. Okay, so I'm going to go ahead and start my graph at -1. And hey, my slope is actually 2 again. So up 2 over 1, up 2 over 1. Even if I didn't use a ruler, and it kind of looks like these are going to intersect, I know for certain that these are not going to intersect. Why would I know that these are not going to intersect? If you answered because these are parallel graphs, you are correct. And we could have actually been able to tell that right away if we had gotten both of these into slope-intercept form, because my slope here is 2 and my slope here is 2. So when that happens, even if we don't end up graphing, our solution is actually going to be no solution, and you don't need to verify it. So finally, the structure of a problem. So what is it about the structure of equations that leads to one solution, infinitely many, or no solutions? This should start to be a review for you guys. Type of solution. Let's start with what we know. So we just did no solution. So here I can say that the equations are parallel. And an example of system of equations in slope-intercept form, go ahead and write 2 equations that would be parallel. Doesn't matter what they are. I'm just going to write y equals 2x plus 1 and y equals 2x minus 3. I wrote it with small numbers because we're going to put these on the graph. So if I start at 1, I go up 2 over 1, up 2 over 1, or down 2 over 1 in the other direction. That is my y equals 2x plus 1 line. The only thing that's going to be different about my y equals 2x minus 3 is I start at -3. I'm going to have the same slope, so I'm always going to go up 2 over 1. You must, on a test or quiz, actually plot those points and not just put a ruler there and try and draw a straight line, because I need to see that those points are actually plotted correctly. Infinitely many solutions. So it actually asks us for an example of a system of equations in slope-intercept form. The only time I have infinitely many solutions is when I have the same exact line. And you're usually not going to see them both written in slope-intercept form, but just for the sake of this, let's pretend I have y equals x plus 2. The other line would have to be y equals x plus 2. So if I start my graph at 2 at the y-intercept, my slope, when there's not a number in front of x, my slope is just 1 over 1. Remember, because we don't write that invisible 1. So that's my first line. If I were to graph my second line in a different color, it would be the same exact line. So that's what I'm saying about however many times those graphs intersect. They have the same slope and the same y-intercept. Okay, I should actually come back up here and write that these equations have the same slope, which actually makes them parallel. So the thing about one solution is it's most of the time two equations only have one solution, because any two equations that have different slopes, even if they have the same y-intercept, they have one solution. That's it. That's the only requirement. So I could have y equals 2x and y equals half x. Both of those have the same y-intercept of 0. But if I go up 2 over 1, up 2 over 1, or down 2 in the other direction, that's one equation. And my other equation is y equals half x. So again, I still start at the same y-intercept, but I go up 1 over 2, up 1 over 2, or down 1 and run 2. Oops, that's a bad line. So my point of intersection just so happens to be the y-intercept in this case. That won't always be the case if they had different y-intercepts. But the only thing that two equations need for one solution is different slopes. So that's the end of 4.1c lesson. Don't forget to do your 4.1c homework as well by next class. I will see you guys next class.